In this section, we will look at another boundary value problem in plane elasticity, and that is a line load acting on an infinite half plane. It's also called the Flamand problem. So the geometry is shown here. The half plane extends infinitely in the x and y direction. In the z direction, it is immaterial because we are going to take unit thickness and consider it as a plane problem. My x-axis is to the left and y-axis is downward, and the r theta coordinates are also indicated here. We have one line load P per unit thickness acting along the y-axis on this xz surface, and another line load Q per unit thickness acting along the x-axis again on the xz surface. Now we will try to solve for the stress field in this case. It can be either plane stress or plane strain. What are the boundary conditions for this problem? On theta is equal to 0, sigma theta theta and sigma r theta are 0 except for the point r is equal to 0. Similarly, theta is equal to pi, sigma theta theta and sigma r theta are again 0 except for the point r is equal to 0. Now let us look at a small semicircular portion of the domain as shown here, having a radius a. This I have explained in my very first lecture on experimental stress analysis in the context of a beam with a concentrated load. So there will be a distribution of traction on this semicircular surface. The traction can be expressed as shown here. Now the resultant of this traction taken over the entire semicircular surface should balance the two line loads P and Q. So if you remember my first lecture, this will give you a 1 over r type of variation for the traction, or the stress component should vary as 1 over r. Keeping this in mind, we can choose the Airy stress function as shown here from the Mitchell solution. So there is a log r term, there is a r theta term. Now once you know the Airy stress function, you can express the stress components in terms of the Airy stress function. If you do that, you will get these equations here for sigma rr, sigma theta theta and sigma r theta. Now you use the boundary condition that sigma theta theta and sigma r theta are 0 on theta is equal to 0 and pi. Then you will see that the two constants a12 and b12 vanishes, or the stress components sigma theta theta and sigma r theta are identically 0 everywhere in the domain. So you are left with only one stress component sigma rr, which can now be written in this form here, involving two unknown constants b15 and a15. To determine these two constants, we will use the condition that you take any semicircular part of radius a and consider its equilibrium. The resultant of the traction on this surface should balance the line loads. So you get one equation like this. This is for the horizontal component of the resultant, which will give you b15 is equal to minus q upon pi. And if you consider the vertical component of the resultant, you will get the second equation shown here, which will give you a15 as p upon pi. So essentially we have solved the stress part of the problem. If you assemble everything together, you will get sigma RR as shown in here, and sigma theta theta and sigma R theta both are 0. So interestingly, you will note that for both the vertical load P and for the horizontal load Q, only sigma RR component is non-zero. Sigma theta theta and sigma R theta vanish. And you will also see that, as expected, there is a 1 over R singularity for sigma RR when R approaches 0. Now let us look at the special case when Q is 0, there is only one vertical line load as shown here. In this case, the stress component sigma RR will be minus 2p upon pi r sine theta. You consider a point as shown here, r theta, and draw a circle passing through this point and the point of load application as shown here. Now you connect this point to the circle where it intersects the y-axis. You will immediately notice that r is nothing but d times sine theta, or r by sine theta is d, the diameter of this circle which we have considered passing through this point. That tells us that on this circle, anywhere on this circle, r by sine theta is d, which is the diameter of this circle, and sigma RR is minus 2p upon pi d and remains constant on this circle. You can consider circles of different diameter, and on each of these circles you will get a particular value of sigma RR which will remain constant on that circle. Now sigma R theta is 0 everywhere, so sigma RR will be one of the principal stresses and it will be the minor principal stress because it is negative. So now you can imagine how the isochromatics will look in this case. What will be the shape of isochromatics? I can do a stress transformation and express the stress components in the xy Cartesian coordinate reference, and you will obtain this expression for sigma xx, sigma yy and sigma xy, and you can see that all these three components becomes unbounded as you approach the point of application of load.